All right, this is my second go around at 3.8, exponential growth and decay. Last time I accidentally hit escape before it was done saving, and we just need to put that on the list of things not to do while using this smartboard recorder. Okay. So exponential growth and decay. Remember our exponential growth and decay functions we had back in pre-calc A. Okay. And so whenever we're looking at differentiating an exponential growth or exponential decay function, all we have to do is simply take our growth factor, k, and multiply it by this y function. Now, what we saw in pre-calc A was that if k was greater than 0, we call it the law of natural growth. If k is less than 0, we call it the law of natural decay. So the only solutions of the differential equations are going to come from the exponential functions, which is y of t equals, I think we did y sub 0 last year, where this is just my initial value. So if we're talking about population, it's just my initial value of the population in a year. I got an example coming up, but e to the kt. And some of you just took out the y sub 0 and you put in a p and you just use the PERT equation. More coming on that at the end of this video. We'll kind of see where it comes from. It's really neat. So let's work one that is population growth. So if I'm trying to differentiate my population with respect to time, this 0.02 would be my growth factor, k. So it's growing at a rate of 2%. And I would just multiply that by my population at whatever time I'm interested in. And that would tell me the instantaneous rate of change of the growth. So if the population at time 0 is p sub 0, then the expression for the population is going to be given as such. And what I want you to see from this is just that 0.02 just went right in where that k, or if you're using an r, right where that rate of growth goes. So what we're going to do is we're going to work this example one. We're going to use the fact that the world population was, this is kind of weird to me, 2,560 million, which would be the same as 2.56 billion, but they wanted to put it in millions, I guess, in 1950, and 3,040 million in 1960, to model the population of the world in the second half of the 20th century. Assume that the growth rate is proportional to the population size. I want to find the relative growth rate, and I'm going to use the model to find the population in 1993. And it says predict the population. I guess I need to change this because it is the year 2020 when I'm making this video. So you'll probably be watching this in 2020 or after. But it would be used at the time this problem was written to predict the population in the year 2020. So I'm going to go back and I'm going to use my population at times t is equal to the initial population times Euler's E raised to the growth rate times t. Now there's a couple of things they told me up here that I'm interested in. I'm going to use this as my initial population. That's the first population they told me. I don't actually want to go all the way back to Adam and Eve or population of 1 or anything. What I'm going to do is I'm going to find a nice year, or maybe even find the first year that they tell me. I say first year, that's kind of a misnomer. The earliest year that they tell me. And so from there, I would then know that 10 years later, my population was 3,040 million. So let's plug in what we know. We know that in 1950, the population was 2,560 million. I'm just going to do 2,560. Millions will be in my units. So that's my P naught. Okay. I don't know what K is. I have to find it. And the only other information I'm given is the fact that 10 years later, the population grew to 3,040 million. And so what I can do now is I can solve this for K, and I will get my growth factor that I need. So I'm going to divide both sides by 2,560. Mhm. I just left that as a fraction. So I'm left with e to the 10k. Let's go ahead and write that. And that's, you could do 304 over 256 here if you wanted to. And to get rid of that e, I'm going to take the natural log of both sides. And that's going to equal 10k. If I divide both sides by 10, my k is going to come out to be around 0.017185. Keep several decimal places on there for me because when we're dealing with exponential growth, just keep rounding off your decimals too early can really change your answer. So keep several for me. I like 6. That's kind of been my rule of thumb whenever I teach pre-calculus and calculus. Okay. So now what that gives me is it gives me this formula now. My population at time t is going to be based off my initial population, 2,560 million, e to the 0.017185t. And so now I can find the population at any time that I need. I can find the population in 1993. Now be careful, don't go through and plug in 1993 in for t, because that would mean because remember t equals 0 is actually 1950. So 1993 would just be 43 years later. So I got this nice explicit formula where I can just plug 43 in for the exponent. So I did that. I got 5,360 million people. Okay. Let's see if we can extrapolate a little bit. Go ahead and work 2020. Hit pause on the video and plug in 2020 and see what you get for what the population should be in this year. So for 2020, I had to use 70 for my t because it's 70 years after my initial year, 1950. And I got 8.525 billion people. Let's work it the other way. Oh, I missed some of it. All you Erase All fans, I apologize. Created more work for myself. So whenever I'm dealing with the half-life of radium, remember half-life is just going to be the amount of time it takes half of any given sample to dissipate, to decay, I guess would be a good word to use since we're talking about decaying. And so if we're talking about the mass, this time instead of population, I'm going to use M of t. And I'm still going to have an initial mass. I'm still going to have a growth factor. And it's all going to be based off of time. The only thing that I should notice on this one that's going to be a little bit different is that my k should come out to be negative if I work it right. And some books will tell you to go ahead and throw in a negative in for that k, and you can work it out. That's perfectly fine. That just means your k is going to end up being positive when you plug it back into a negative. I just work it out normal using the same formula. Okay, so it says a sample of radium 226, that's just its number, has a mass of 100 milligrams. Find a formula for the mass of the sample that remains after t years. So it's just wanting a very generic form for it. Okay, so part A right here, a mass of 100. So that's going to be its initial quantity is the 100. I don't know what K is, but I know that if its half-life is 1,590 years, after 1,590 years, I'm going to be down to 50 grams. That was my definition of half-life. And I can use very similar math to solve this for K. All right, so I can divide both sides by 100. That simply gives me 1/2. Take the natural log of both sides. Left my K off. Not do it again. and then divide both sides. I'm going to get something really small here. The book actually just left it as an exact answer. So natural log of 1 is 0 minus natural log of 2 over this 1,590 equals k. So you're more than welcome to leave it like that. I think in the last video I went ahead and decimaled it out. But my mass at time t is going to be equal to my initial amount, 100, e to the, let's decimal it out. I think most of you will. Here we go. Peyton left her calculator right here for me. Let's see. We got negative natural log of 2 divided by, it's going to be a really small number. So I got like negative 0.00043 594. Is that enough? It's a pretty good number of decimals. Maybe a 2 in the end. Got six figs there, and that'll work. And so if I'm looking to find the mass after 100 years, that's what we just did a while ago. I just plug in 100 in for my t, which I left off again. Man. All right. After 1,000 years. There we go. And so whenever I did this earlier, I got right around about 64.7 milligrams. Might be a little bit off because of my rounding on there, but not too far. All right, let's look at part C. All right, part C, I'm wanting to find when the mass will be 30 grams. That means I'm going to plug a 30 in for my mass side. I just erased my long decimal. I remember it was negative 0.0004359. 1, is that enough? 1, 6. 1, 2, 3. Yeah, that's good enough. T. And so I luck out here because my math for this is going to be very similar to what I did in part A. Remember in part A, I was solving everything for K. Now I'm just solving for his next door neighbor, T, right here. And that will tell me how long it's going to take. So my math is the exact same. I'm going to divide both sides by 100. That's going to give me 0.3. I'm going to take the natural log of both sides, natural log of 0.3, and then divide it by this horribly long decimal. And that's going to give me T. Okay, so that's my exact answer for T. Whenever I worked it out earlier, it said it's going to take like 2,762 years for it to get down to 30 grams. It's a long time. I won't be around waiting on that one. All right, now Newton kind of played around with some of this stuff, and he came up with a law of cooling. Newton said if we let T of t, the temperature at time t, be the temperature of an object at time t, and T sub s be the temperature of its surroundings, then we can formulate Newton's law of cooling as a differential equation. Now here's a problem though. The differential equation is still going to have K in there, but you're going to have to subtract off the temperature of its surroundings. Okay, so this is going to work a lot like an exponential growth or exponential decay model, but you've got this little added idea right here that we're going to have to subtract off the temperature of the surroundings, and I'll try to illustrate that a little bit if I can. See where we get with it. Okay, so suppose you're throwing in a bottle of soda pop. I think that's what they call it in Kansas, is pop. at room temperature 72 degrees. So I got this warm soda. I'm placing it in the fridge where the temperature is 44 degrees. After half an hour, the soda pop has cooled to 61 degrees. Part A, what's the temperature of the soda after another half hour? Well, the benefits of working in here in my classroom by myself right now, where no one can holler out the answer, is that I don't have to sit there and say no, the answer is not going to be 50 degrees. Everyone wants to say 50 degrees because obviously if it drops 11 degrees here, another half hour, it drops 11 degrees, we're going to be at 50 degrees. But that's not how it works. Let's think about the temperature in your fridge. Suppose that this is my 44 degree mark going across right here, and I threw in the soda at 72 degrees way up here. Now let's talk about what the line's not going to do. The line's not just going to go boom and then stay at 44 degrees, right? What does it do? The line kind of comes down fast at first, but then as I get closer to that 44 degree mark, it starts leveling off more and more. Okay, so yeah, it does go down a lot at first, but after another half hour, I'm willing to bet it doesn't drop 15 degrees again. Is that 11 degrees, I'm sorry, down to 50 degrees. So to account for this, what we have here is we have shifted everything up 44 degrees. So what I'm going to do is I'm going to, let's see how this works. Nope, not that one. I'm going to take my whole graph right here, and I'm going to shift it, try to make it so that asymptote just moved. I'm going to shift this 44 degrees down so that it's down here on the axis, and that these graphs just come down to there as well. I don't know what's going on anymore. All right, good news. If you don't understand any of that, I'll just make sense of it down here with the math, and you can go back and listen to me ramble about it later, okay? So what I'm going to do on part A right here is I'm going to change all of my temperatures to degrees Fahrenheit. I'm going to change it to something called, I'm just going to call it degrees Kurt, okay? And my degrees Kurt, I'm going to let that be Y. And to get to degrees Kurt, I just take whatever the temperature is and I subtract 44 degrees. That's going to make it so that horizontal asymptote comes down to the x-axis. All right, so what we got now? So now we got that the initial temperature, because I'm going to need my initial temperature since I'm doing this exponential decay, is going to be whatever the initial temperature was minus 44 degrees. So this 72 degrees that it started off in the refrigerator, I'm going to change that to degrees Kurt, and I'm going to call it 28 degrees Kurt. So now I'm able to write my function in degrees Kurt. My initial temperature is 28 degrees Kurt. I'm looking for the K after time t. And so I'm told that the temperature drops to 61 degrees after 30 minutes. Well, I need to put that in degrees Kurt. 61 minus 44 is 17 degrees Kurt. So it drops to 17 degrees after 30 minutes. I could easily have done 1/2 right there and just remember that we're talking in hours. I'm going to put all of my t in minutes on this one. I have very similar math on this. I'm going to divide both sides by 28 and take the natural log. That's going to give me natural log of 17 over 28 equals 30k. Divide both sides by 30. My k came out to be negative 0.01663. So in degrees Kurt, my formula is going to be a function of time. It's going to be the 28 degrees Kurt e to the negative 0.01663 t. However, I've tried and tried, and I have not got the National Weather Service to actually acknowledge degrees Kurt as a unit of measure for temperature. So what we're going to do is we're going to take it back to the temperature in degrees Fahrenheit. And so to take it back to degrees Fahrenheit, I'm going to shift everything back up 44 degrees. Oops. 44 degrees, up 44 degrees, back to where it was. And that'll put it back in Fahrenheit. Haven't even answered part A yet. What is the temperature of the soda after another half hour? Another half hour would be the 30 minutes that it was in there plus another 30 minutes. It'd be the temperature of the soda after 60 minutes. So if I plug in a 60 in for that T, I got it to be 54.32 degrees, which makes sense. I told you it wasn't going to drop all the way down to 50 degrees because it's going to level off. All right, so it leveled off a little bit like the green line at the top shows, and that would be the temperature after another half hour. How long does it take the soda pop to cool to 50 degrees? All right, I'm going to erase part of this. I'm going to let you work that out and see what you get. So go ahead and hit pause, and then I'll work it out over here on the side, and you can see if you get the same thing I did. I got about 92.63 minutes on that. It'd be about an hour 33 if you worked it in hours instead of minutes. All right, lastly, I want to talk to you about continuously compounded interest. But before we get to continuously compounded interest, I want to remind you of some Algebra 1 that you did, probably with Miss Pfeffer, Miss Bowen, whoever you took Algebra 1 with. It says, poor Johnny invested his life savings of $1,000 into an account that pays 6% interest for the next 3 years. Find the balance in the account if it is compounded annually, semi-annually, quarterly, monthly, and daily. We did this last year as well. And so we always said that the annuity was going to equal to the principal plus 1 over Rn raised to the nt, where the n was the number of compoundings, t is the amount of time, r is the rate as a decimal, and then the p still stands for the principal or the initial amount that Johnny put in. So if it's being compounded annually, what Johnny's going to do is he's going to take his $1,000 and they're going to apply the 6% interest one time for 3 years. And so whenever I put all that into my calculator, I got $1,191.02. Okay. I'm going to go ahead and pause the video and work the rest of these because I think this is just a plug and chug that you can do. And then you can do the same, see if you match up. And I want to talk about what happens after daily. Okay. So over the course of time, you see that when poor Johnny goes from compounded just annually, compounded to compounded daily, he's gaining about, what, $6.18? And it's not a lot over 3 years. It's an easier way to probably make $6.18 than just money sitting in the bank. That's not bad. But what I want you to notice on this is that as I go, I'm getting limiting values here. At first I jumped, what, $3.03, then I jumped $1.57, and then I jumped from green to blue here, $1.06, to where I'm just jumping less than $1 if it's getting compounded monthly versus getting compounded daily. And so I'm getting closer and closer to a value here. And so I want to illustrate what this value is. So what I'm going to do is I'm going to come up here to my original equation for finding compound interest, and I'm going to raise it to the first power. Well, raising it to the first power does not change the value of it. So I'm going to change that first power to an r over r. And so what that's going to do is going to allow me to rewrite some stuff. Okay, so I still have my principal amount. And again, what I'm wanting to see is the limit on this. So I see that the only thing that's changing is my n. I'm compounding it more and more and more and more. Well, what if I just go ahead and compound it an infinite amount of times? 1 plus r over n raised to the, I'm going to grab this n right here and this r. I'm sorry, the bottom r and the bottom r. There we go. And then that's going to leave me with RT on the outside. And everything to do with the limit, so I can throw it out. And so what I want you to do in your calculator is I want you to think of a really big number. I'm just going to use 1 million. Okay, so suppose this thing's getting compounded 1,000,000 times. Hey, let's just go bigger. Let's go 10 million. So I want you to, in your calculator, I want to figure out what this part in parentheses is, this limit. So take your rate, this 0.06 right here, and divide it by 10 million, or go 100 million, or just fill up your screen with nines. I don't care. Now that's going to give you a really, really, really small number. So now add 1 to it. That's going to give you 1 point something really small still. And then raise that to the 10 million, whatever number you're using, divided by 0.06. And hit enter. Does that number look familiar? 2.7 something. Hope it looks familiar. Euler's E. So to compound the amount of money poor Johnny's putting into his life savings continuously, I just use my PERT equation. That's where it comes from. And so he takes his $1,000. You just put in the 0.06. You don't have to worry about any ends. They're all factored into this number E down here for 3 years. And what you're going to see is that poor Johnny didn't really make a lot more money. It's kind of sad. I got that he made $1,197.22. Only 2 cents more than if it's getting compounded daily. But that's kind of the, back when we did tables, we saw limiting values. We're getting closer and closer to a value. This is the value that my compound interest is getting close to. I think that's neat. I like always working that problem with you guys in class, so hopefully you'll be here for it. All right, my goal is to let this whole video load before I do anything to my computer. So I'll have to redo this again, but there's your problems. Make sure it matches what I have in Google Classroom or whatever we're using. Hope you guys have a fantastic day. I'll catch you guys next time.